virtually even. I hope I can come in person and see many of you. Had some great chats today already. I look forward to maybe chatting with some of you tomorrow. Yeah, this is an indulgent talk for me because obviously, as you heard in the introduction, I often work on exomoons and exoplanets more generally. And I was very torn as to which talk to give today. I thought I'd talk about this just because I had a paper about it recently. And I think some of the points here are broader. I know exomoons is kind of niche. And if you're interested in galaxies, you probably won't be so interested in hearing about exomoons. So I think I chose this talk because I think it's a bit broader, it can bring us more in. And it talks about this kind of controversial subject of what do you do with one data point? And in particular, it has a lot of applications to astrobiology. So I'm going to focus a lot on the astrobiology in this talk, but we'll come to a more general application to broader astronomy as I go. So if you're just interested in that part, you can just sort of tune in for the last 5 minutes for that bit. But I think the astrobiology case is particularly interesting, just because it's a question that you see in headlines all the time, and it's often an abused point. The first thing I want to say about the statistic of one is that you often hear it said, even by some astronomers, that one data point teaches you nothing. And that's not true. I think we can just want to dispel that right off the bat. 0 data points teaches you nothing. That's the definition of 0 data points, no information. And nothing like magical happens when you go from 1 to 2 data points. Of course, the more data you accrue, then the easier it gets to do your inference. You're becoming in many ways less subjective to your choices you make in your analysis. And that's why big data and data intensive science is so popular these days. But for me, the statistic of one has a peculiar intellectual appeal because you can't be lazy. You're in data, with huge data, you can kind of be lazy. The data leads the way, it guides you. With one data point, you have to think really carefully about the choices you make. It makes a really big difference as to what you choose, as to what you get out. So that's what kind of drew me towards this subject. So we're going to talk about astrobiology. I'm going to frame it a little bit in terms of the Drake equation. The Drake equation, of course, is really just an organizational principle. I'm not going to go through it because we all know what the Drake equation is, but this is just going to be sort of our context as to how we're talking about this problem. And in particular, I'm going to focus right in on FL, which is the fraction of Earth-like planets that go on in this equation to form life. And it's sort of, you can treat it however you want. Think of it as an average over all of the Earth-sized planets in the habitable zone, or depending on the number of rare Earth hypothesis people out there, you can just frame it in terms of those objects. Again, it's not particularly important for this discussion. For me, I'm really interested in just the Earth. If you took the Earth and you reran Earth's tape back, how often would we expect to get successes? And then that maybe provides some context for if we did have these true Earths out there, how often would we expect life? Okay, so just looking at this term, this is, hopefully the sound's going to work here. You'll hear a few clips. This is what a lot of popular sci-commers will often say about this. And I think this is important because it informs a lot of the public discussion about this question of life in the universe. And honestly, the views here are not controversial. In my experience, these are the most commonly held views amongst my colleagues. So I want to share this. Can you hear this? No. I don't okay, I'm going to have to narrate it then. So they're asking Bill Nye, Brian Cox, Neil deGrasse Tyson, what do you think the chances are of there being life in the universe? And each response is basically, of course there is. What a stupid question. There's 100 billion stars in our Milky Way. So naturally, it would be so contrived. It'd be so contrived for there not to be life elsewhere in the galaxy. And pretty much all of them are saying the same thing. And really, you can counter that with a very simple tweet even. And Sean Carroll did so here in response to Elon Musk, who is perpetuating this. And he just points out, well, that's not necessarily true. If the probability of life starting was 10 to the minus 100 on each planet, then trivially, you could have basically an almost empty universe, depending on your definition of universe, observable universe, or if you go out to infinity. Eventually, you'd hit something. But certainly just in our galaxy, if the probability is less than 10 to the minus 10, there's pretty much no way there's anybody else out there in the galaxy right now. So this is kind of not a popular opinion, and you might say, well, 10 to the minus 100 is fine-tuned. But in another way, having a number between 10 to the minus 10 and 0 is also just as fine-tuned as having a number between 10 to the minus 10 and 10 to the minus 100. In many ways, in a logarithmic sense, there's more space below than there is in that intermediate region. So there's no good argument as to why it can't be 10 to the minus 100. But the common rebuttal to that you might hear is, think about Copernicus, the Mediocrity Principle, and say, well, we're here, and so we're not special. And often you hear people say, like, it's arrogant. Or, they bring in emotional terms here. It's arrogant or it's egotistical to assume. And to me, I don't really like to use that language, because it's kind of trying to persuade people by an emotional appeal, really. Because people are, well, I'm not arrogant, I'm not egotistical, so I must agree with them. And I'd rather just talk about the math and the science rather than trying to make emotional appeals about specialness. But the Copernican principle is essentially this, that we're here, therefore others should be. And I want to give you an example as to why this really doesn't work. So let's imagine we have an urn, we fill it with some balls, and I don't know the color of these balls in the urn, but I'm going to pick them out. But the rule is, if you pick a ball that is not green, you're going to be immediately shot on the spot, and we'll never, it's a very sadistic experiment, we're never going to hear from you again. Okay, and so eventually, you're here now, you're alive now, so you must have picked a green ball, else we would have shot you as soon as you became aware, self-aware entity. So you picked a green ball, and now I want to ask you the question, how many green balls are in the urn, given that A, you picked a green ball, and B, had you not picked a green ball, you wouldn't be here to talk about it. Now, it doesn't matter how good you are at statistics, you won't be able to work that one out, because it's an impossible problem. There's no way you can figure out how many green balls are in that urn on those conditions. And this is just the same thing that we're doing in the galaxy. I mean, there's all these worlds out there. Some of them are living worlds and some of them are dead worlds. And what is the probability? You have picked, clearly on the Earth as a living world. You picked a living world from the galaxy. How many living worlds are in the galaxy, given that you picked a living world, but you had no choice but to pick a living world, else you wouldn't be here to talk about it. Exactly the same problem, just reconceptualized. There's, again, no way to formulate this or to make mathematical progress. In a very general sense, the Copernican principle doesn't work when it concerns statements upon which our existence is predicated. So it works perfectly fine if I was talking about exomoons, because whether there's exomoons in the universe or not, my existence is not dependent upon that statement. But whether Earth-like planets go on to form life, that's a statement upon which my existence is predicated. And so I can't make useful statements about that. However, if we go beyond just existence, there are aspects of what happened on Earth that maybe could be used with the Copernican principle. And in particular, the next thing people might point to is the timing of life. So as many of you, I'm sure, realize, life happened very quickly on the Earth in the geological scale of things. It happened within the first few 100 million years. And this is often highlighted as a sense of optimism, that there must be therefore life elsewhere. So let's look at this timeline and figure out if this makes sense. So we have I'm going to call it time equals 0, when the Earth became habitable. That was about 4.4 billion years ago. And this essentially is when the oceans form. So we see look at mineralogy, you can tell there's evidence for oceans 4.4 billion years ago. Going forward, we see the first evidence for life. It's controversial evidence. It's not widely agreed upon. But 300 million years later, you see an excess of carbon-12 over carbon-13 in zircon deposits. And as you probably realize, life prefers to work with carbon-12 over carbon-13 when it can. It's just energetically easier to work with. So that imbalance has been suggested as evidence for life. The most unambiguous evidence for life comes a bit later on, though, 900 million years, when you have actually microfossils. Of course, then we get eventually to us, humanity. And you could say, well, when do you find that? Is it when we have hominids, which is about 2 million years ago, a few million years ago? Or is it when we started farming? Is it when we started radio signals? It really doesn't make any difference on this scale. You can move this number around by 2 million years and you would just change 4.4 to 4.398. It really isn't going to make much difference how we define intelligence. In fact, really, even going back to multicellular life, the emergence of multicellular life was at 3.8 on this scale. So you really have to go very, very far back to just when you started having two cells stick together as your definition of intelligence to significantly move this data point very much, depending on definitions. And then finally, we know the Earth will not be hospitable to complex life forever. And actually the evolution of the sun is going to bring an end to it, probably far shorter than our intuition might guide us from astronomy. We often think of the red giant phase as maybe being an endpoint, but actually the sun's gradual warming will lead to a termination of the long carbon cycle, the slow carbon cycle, after about 0.9 billion years in the future, at least as estimated by this paper by Caldera and Jim Casting. So there's a finite window, and it's kind of interesting that intelligence emerges quite late on. Okay, so with this data in mind, let's come back to this original question. Life started early. So let's imagine that the time it took, this is a thought experiment. Let's imagine that the time it took intelligent life to emerge on Earth-like planets is always as long as it did on the Earth. So it took about 4.1 billion years on the Earth, and that's pretty much the minimum time it takes, or it could even be longer. Well, if that were true, then I could push this needle back to a 1.2 billion year start date and still have time for intelligent life to emerge before the end point of the Earth's habitable window, basically. Okay, so therefore, if we are here, if we exist, then life would have had to have started early for us to exist. There's no two ways about it. Otherwise, we wouldn't be here to talk about it if that statement were true. So if the minimum time needed for intelligence is greater than or equal to how long it took on the Earth, then life starting quick is actually a requirement to our existence. And therefore, it's not interesting because we wouldn't be here to talk about it had it not happened. We can't use it as a useful data point. It has been sculpted by a very severe selection effect. What if the opposite were true? Because that's just one example. What if this is the minimum time needed for intelligence to develop? That intelligence evolution, we can go from abiogenesis to something thinking and being able to do statistics and geology and paleontology, multicellular complex life, all that jazz. All that can happen in, say, less than 1 billion years. But if that were true, then, first off, that would be pretty surprising because clearly that didn't happen on it. We didn't even get multicellular life until 3.8 on this scale. So we would be very, very slow an evolutionary example in the universe if this were true. But let's just work with it. If that were true, then life indeed could start very late and still have time to develop intelligence before the end. And so in that case, you would say, well, life doesn't have to start early. There's no requirement for life to start early. And therefore, life starting quick isn't a requirement, and therefore life's quick start is interesting. In that case, it really would be interesting because it's not necessary for our existence for life to start early. Its early start is a data point telling us about how easy abiogenesis intrinsically is. So these are the two cases, but this top one, as I pointed out, is inherently suspicious because it's kind of inconsistent with the example of evolution that we saw on the Earth. And that's not just driven by complex life. It's all of the transitions in the evolutionary history as well, which clearly also took the eukaryote evolution, combogenesis, photosynthesis. All of those transitions took many hundreds of millions of years to evolve. So we might have some suspicion about this. And therefore, the quick start to life is maybe not as useful a data point as we thought. And what I want to emphasize here is that this is clearly tied in. It's covariant to the evolutionary timescales of intelligence. You can't talk about abiogenesis timescales without talking about evolutionary timescales. That they're married to each other. I could see a hand raised.
Yeah.
Do you want to ask your question?
I have
a question.
Yeah, if I could ask it. So in this context, I mean, I find what you're saying very compelling, but I was wondering if this was contingent on other processes being present, such as, say, the long, violent bombardment of the early Earth's history, right? So how, there is presumably some interplay between whether or not life's early start is interesting or not interesting with the kinds of processes that would just prevent an early start from really taking root, right? And so I was curious if that mattered or not.
Oh, I think it would. Essentially, what you would do, and this is in a very general sense as well, not just about the Late Haven bombardment, for example, you can revise the date, right? So you could push either that start, the 0 point forward, or you could even push the earliest evidence for life back. In either case, you're just changing that data point. And as I'll show you, if you bear with me, you will see how that revision act will be important actually, and could be one of the best ways to improve this. So I think if we hold our horses, we'll get to that. Yeah. I want to talk about this paper because this is the paper that is probably the most famous on this topic. It's a seminal paper, and it was the first to frame this in a Bayesian framework by Spiegel and Turner. And they really took to task the early start to life and tried to more rigorously ask, what does it really mean? I'm going to go through it quick, but I just want to ask two questions. What did they do and what did they find? Okay, so we're going to do a bit of math here. I'll run through it fairly quick, but there is going to be some derivation here. First off is what in any work, there's assumptions, especially in a simulation modeling regression problem, there's assumptions. And here they basically made three big assumptions. The first big assumption is that abiogenesis is intrinsically a stochastic process. It's a random process. It's not deterministic. And specifically, it is a uniform rate process. So from going from time equals 0 to time equals 1 million years, the probability of life starting is the same as from 1 to 2 or from 1.5 to 2.5. In any interval, the probability of abiogenesis is the same. So that defines a Poisson process. If that's true, write down the probability distribution like this. So we have the number of abiogenesis events, n, given a rate of abiogenesis. We have to have some rate, and that's ultimately what we're trying to infer, over some time interval. So what kind of times are we talking about? So you just have the normal Poisson distribution. Now, we don't actually know how many successes there were. We only know there's at least one. There could have been actually dozens or millions of the things, as far as we know. We can only see one, and even if there were multiple other examples, by Charles Darwin wrote about this, they could have all just been outcompeted, and that's why everything seems to be universally related these days. So we know there's at least one, so we can just take basically the sum over 1 to infinity of our Poisson. And this is the probability of life emerging by a time t, since it's over an interval, by a time. And since it's by a time, really you can think of it in a temporal sense of being a CDF. It's a cumulative density function, since it's an integral from 0 to time equals t dash. So to get the actual probability distribution of the time itself, you have to take the derivative of that, the PDF. And then we end up with this, which is basically an exponential distribution, which should make sense. If you know anything about Poisson events, you probably know the time difference between them is distributed as an exponential. However, we have a selection effect, and that's that we can only count events if they occur within a time tau. So this is like the evolutionary time scale, essentially, in Spiegel's model. So it has to happen within a time tau, or otherwise we don't know about them. And so that's just you're just basically renormalizing over a time interval tau. And finally, we actually don't know that life emerged at a certain time t obs. We only know that it emerged before a time t obs. When we see microfossil evidence, that's not the date when life started. Life would have had to start before then to have had some time to develop those fossils in the first place. So that's only the upper limit as to when life started. So you have to do an integral. And finally, you end up with this function, which is their likelihood function. So now they can make statistical progress. They can ask, what is the probability of getting t obs, the time at which we emerge life in the geological record, is described by this function. And they're trying to figure out lambda. That's what they want to know, lambda, which is the rate of abiogenesis. So, and remember that tau is the selection effect. That's the mean time it takes to evolve something like us that can do statistics. So they apply Bayes' theorem, very familiar, won't go through this. It's a posterior, there's that likelihood function. And now we get into their other assumptions. Assumption 2 is, what do you do for this tau thing? What is the evolutionary timescale? And they really got stuck here. They didn't know what to do with this. They just pretty much assumed two fiducial numbers, 3.5 billion years, which is kind of roughly how long it took on the Earth, and then a much more optimistic 1.4 billion years. But they're really are fiducial choices. The third assumption is the prior. Anyone who knows anything about Bayesian statistics knows that priors are the bane of our lives, and priors here are particularly painful in terms of their impact on the robustness of the results. They chose 3 priors: uniform, log uniform, inverse rate. Seems pretty plausible, what most of us do when we don't know much else. Okay, so this is their results. Rules are basically, we don't know. You change the priors between these 3 different guesses, in green, blue, and red. The dashed line are the priors, the posteriors are in solid, and you can see they're pretty similar, but most importantly, they're radically different between each other, right? Between 3 different priors, you get radically different posteriors out. And so their conclusion was the results are sensitive to the priors, which is basically always true. I mean, whatever you're doing, the results are always in a Bayesian inference, they have to be sensitive to the priors. It's impossible for results to not be sensitive to the priors. But the results here are particularly sensitive to the choice. As you can see, you get radically different answers. So I appreciate the dog there. I appreciated that point. So can we do any better than this? So here's the landscape of what was done. We have two different choices for tau, 3 different priors, so 6 different realizations. And here are my critiques of what they did. And this is going to provide a pathway forward. So critique number 1, look, just choosing these 2 different evolutionary timescales is arbitrary. We really don't know they're the right choices. And look, if you're going to all the effort of trying to infer the rate of abiogenesis, why not just go the extra step and also try and infer the rate of evolution at the same time? Just have 2 parameters in your model rather than 1. Now, I know that seems scary because you're adding more unknowns into a very poorly constrained problem, but actually I would argue it's the best thing to do because you're actually propagating your ignorance about that term because there will be covariance between them as we've discussed. And so that's going to inflate your uncertainties in an appropriate way rather than giving you artificially narrow posteriors at the end. I know there's no risk, you might think there's no risk of that given what you've seen so far, but I do think it makes more sense to propagate everything you don't know into the model rather than just choosing arbitrary choices. Critique number 2 is these priors. Now these priors they're not objectively defined, they are subjectively chosen. And instead of doing that, I'm actually going to show you a trick where we can get rid of the priors altogether and your priors won't even matter through a bit of kung fu, basically, on the statistics side. Now, what I want to point out there is that many people who read this might immediately say, David, hold up a second. You're claiming these are subjective priors, but they're not because they've got a log uniform prior in there. And many people that think that is the Jeffreys prior. They can talk about that as being a Jeffreys prior. And Jeffreys prior is, if you look at Fisher information theory matrix, you can take basically the determinant of that and it gives you an objectively defined reference prior for a distribution. However, the Jeffreys, that's basically not true because the Jeffreys prior is not or I should say the log uniform prior is not in general the Jeffreys prior. It's a special case with a particular set of conditions. And in particular, it's only true if you know the minimum and the maximum, lambda min, lambda max. You look at the bottom there of my slide. So if you know the minimum and the maximum of some process or some parameter, then indeed you can show that the reference prior is a log uniform prior. If you don't know what those numbers are, then this all falls apart. It's not true anymore. And it is completely arbitrary. I mean, we don't know that the minimum rate of abiogenesis is 10 to the minus 3 per gigayear. We don't know that the maximum is 1,000 per gigayear. We have no limits that we can reasonably put in here. These are just completely arbitrary guesses. And so if you're making arbitrary guesses about the minimum maximum bounds, you have an arbitrarily defined prior. That's not an objective prior. So that's kind of my critique of this paper. So these are made up bounds, and this is a concern. Okay, if nothing else, I want to convince you at this point that the issue of priors is important, and it's actually a major problem. It's clearly a major problem in making mathematical progress. It is how we deal with the priors. Okay, we have a hand raised again. I just want to kind of explain, and then we'll have time for priors, because this priors thing is going to go away. So I don't want us to get too hung up on it because I'm going to show you a trick to get rid of it. I'm going to link to or reference an example by John Haldane about this. John Haldane had an interesting perspective. He was a geneticist, a statistician, a famous popular science popularizer from about a century ago. And he considered the following thought experiment. He said, imagine you have many beakers filled with water, and they're of similar temperature, similar purity. They're probably not identical. You can never get them identical to each other, but they're probably pretty similar. And you ask, in what fraction of these experiments will this unknown chemical, let's call it chemical X, that I'm pouring into these beakers, in what fraction of these experiments would I expect chemical X to dissolve in the water? And we could call that F dissolve, kind of like how Drake, in the Drake equation, he has FL, we would have F dissolve here. Now, Haldane said that we should really expect that F dissolve is some very, very small fraction, much, much less than 1, essentially 0. It will never dissolve or hardly ever dissolve. It might have 1 or 2 weirdos in a million experiments, but generally it should be close to 0. Or it will basically always dissolve. But it would be really weird if 50% of the time it dissolved and 50% of the time it didn't. That would be really strange if you saw that, just intuitionally. And so he said that if you use a uniform prior on F, that puts way too much weight in the middle. You're putting way too much weight at F equals 0.5. You need to be putting much more weight on the extremes of this process. So you'd have a prior that looks like this, kind of curls up at the end. Remarkably, even though he didn't know about it when he did this ended up an objective Bayesian called Jaynes later proved that this actually ends up being the reference prior, the Jeffreys prior, of a Bernoulli process. So a Bernoulli process is like a coin toss, and it has some value of the success happening, and he was able to show rigorously. It's a little bit softer than this, but you get more or less the same kind of shape that kind of curls up towards the ends. So this kind of makes sense. And in a similar way, when we talk about the galaxy, or really just rerunning Earth's tape over and over again, we would kind of expect that life is going to be an inevitable process of just the natural initial conditions that the Earth had, or it's an extremely rare outcome that happens on these Earth-like planets. But it would be weird if half of these planets, exactly half, had life and exactly half did not. The universe is either teeming with life or it's devoid of life. It is really the implication of this philosophy. Now, that philosophy is going to be very important. I just want to take a pause and compare what Spiegel and Turner did to what I'm going to show you, but keep that in mind in going forward. So assumption 1, to recap, was that life is a stochastic Poisson process. I'm going to do the same thing. I was talking to Barry about this. I really don't like this assumption, actually. It's my biggest critique of my own work, but it is what it is. Maybe one of you can think of a better way of doing this. Assumption 2 is, instead of fixing the intelligence timescale, let's just fit for it. Let it be another parameter in the model. Assumption 3, rather than trying 3 different priors, we are going to pursue the Haldane perspective to get rid of the priors altogether. They won't have any impact. Now I'm critiquing Spiegel and Turner. I want to emphasize how brilliant their work is, how seminal their paper was. None of this is possible without, you can't iterate upon someone's brilliant idea without that brilliant idea being first put forward. So these are only very cordial criticisms and go forward. I really love this paper a lot. Okay, so let's follow this Haldane perspective and see where it takes us. This is remember our bowl-shaped prior. We're expecting either life happens all the time or life hardly ever happens. And we can actually make it 2-dimensional. We can think about Fi, the fraction of life forms that go on to form intelligence, and the FL, the fraction of planets that go on to form life, as a 2-dimensional surface. And taking that bowl-like shape in 3 dimensions, we would have these hot spots in the corner. And these spots, of course, have equal probability to each other a priori because of the symmetric nature of Haldane's prior. It is symmetric between those 2 extremes. So these 4 possibilities. And these 4 possibilities correspond to, let's give them some names, M00, which means that life is rare and rarely develops intelligence. M10, life is common, but it then rarely goes on to develop intelligence. Life is rare, but when it does happen, it often ends up in intelligence. And finally, life is common and it almost always leads to intelligence. Those are our 4 extremes. And given that the truth is one of these 4 corners, at least that's what we're thinking from the Haldane perspective, then we can just do Bayesian model selection between these 4 hypotheses. That's really the key here, is that we're going to do Bayesian model selection rather than trying to infer lambda. We're going to weigh these models, these hypotheses against each other. Okay, now there's 2 ways of proving this. I'm only going to show you one for the interest of time. You can ask me later about the other, or we can point to the paper, but there's this neat theorem called the Savage-Dickey theorem, which allows you to calculate Bayesian evidences. Bayesian evidences are essentially the probability of a model being correct given the data. That's really what it means, probability of the model given the data. Now, it's often a difficult integral to get at, but the Savage-Dickey ratio is a way of getting at this term in a really beautiful, elegant mathematical trick that's actually very easy to do, and you can use this in all types of science. So if nothing else from this talk, check out the Savage-Dickey ratio if you do any kind of Bayesian work. It's a really useful way of calculating evidences. It only works when you have nested models. So let's consider the entire ensemble here, all of the squares, as our nested ensemble of all possibilities. And the green dots are particular, well, they are the nested locations within that ensemble. So compare to Z00, model 00, against the ensemble. Z is the Bayesian evidence. The theorem tells us that it's just the ratio of the posterior at that point divided by the prior at that point. That's the Savage-Dickey theorem. That's all we need to do. And so the limits here that I'm putting in front correspond to that extreme of the 0,0 case. So if we go through this, it's fairly simple to work this through. The posterior is just the likelihood times by the prior with a constant for the normalization. And so the priors cancel out. And so this is the kung fu. It doesn't matter what you assume for the prior on lambda, the prior doesn't even feature in this, in the evidence weighing. When you do the Bayes factors between these, there is no prior. And so we can pull the K out because that's just a normalization factor, it's a constant. And so all we have to do is say that Z00 divided by the ensemble is just the likelihood of that model evaluated at that point, which should be actually quite intuitive. And then if I want to compare two different corners, then I can do like a chain rule type ratio where I just can do the ensemble on the top and the bottom, it cancels out. And now it's just the ratio of those two likelihoods evaluated in their different limits. And so the prior doesn't enter. So, you can use Tony can use his prior. He might like the log uniform prior. Barry could be a fan of the uniform prior, but we'll all agree on this. When we calculate Z00 over Z10, we'll all end up with the same answer. It'll be agreed upon by all parties, whatever prior you use. That's important. Here's the results. If I take that bottom row as an example of these four corners. So this is the case where I'm being very, very pessimistic about intelligence. I'm saying intelligence is a very rare process. That's this bottom row. I don't know what FL is. And I'm going to show you here the ratio of these two corners. So really what I'm showing you is the optimism case divided by the pessimism case, fast life versus slow life, just those two corners divided by each other. And what you find is that the odds ratio is about 10, given our best estimates for these numbers. But obviously it depends on what you assume. To come back to Dan's question that he asked earlier about, what happens if you revise this date? You can see now the effect of revising. So if you revise this date far back, you become more and more optimistic about how quickly and easily life can start. Now, there's these different lines on here that's a bit confusing. This bottom row corresponds to that thick black line you can see that I'm highlighting. But here's the neat thing. If I go to, you're saying, well, that's just one assumption, David. You've assumed pessimism for intelligence. Let's go a bit higher up, move up those rows. And as you do that, the effect is to go up to those curves, which you can see higher up. So the only impact of being more optimistic about intelligence is that you end up with pushing this curve upwards. And so the Bayes factor that the black line corresponds to is the most pessimistic version you can get. That's the lowest I can make that Bayes factor. No matter what I do, I can't make the Bayes factor less than that number. So this is a lower limit. And so really the Bayes factor between a fast life and a slow life has to be always greater than the ratio of those two corners as a minimum constraint. Okay, we can actually solve this analytically, which is kind of neat. So you can actually plug in your own favorite numbers if you want to have fun with us. So there's the equation. The takeaway is that for 0.3 gigayears, if life started within 300 million years after habitable conditions, you get 9-to-1 odds that it was a quick process. If you're more pessimistic and only prefer the microfossil evidence, then it's a bit more on the fence. You're looking at 3-to-1. Now, in Bayesian parlance, a 10-to-1 odds ratio is normally treated as strong evidence by the Cass and Rafferty scale in 95. That's the canonical scale of how to interpret Bayes factors. So this is not strong evidence, right? So I want to be clear about it. It's almost there. It's not far off, but we wouldn't call this strong evidence in a Bayesian sense that life is a quick and easy process. We have to still be open to the possibility that it is an unusual process. But there is a sense of optimism here, which gets me excited. And what about, the one thing I really want to emphasize as a cautionary tale with this, look at that bottom bullet point. I'm not talking about Gliese 581G. I'm not talking about Proxima Centauri b. I can't apply this to any other planet except for the Earth, because I don't know that Proxima Centauri b is anything like the Earth whatsoever. This only applies to rerunning Earth's tape. Now, if you really do feel like you've got a planet that is exactly the same as the Earth, then go ahead and you can use this. But this is where the rare Earth hypothesis can come in. We just don't know really how often those Earth-like conditions prevail in the universe. The only thing I haven't talked about is intelligent life. Since I've inferred it, I could do the same thing. I could actually do a Bayes factor for fast intelligence versus slow intelligence. And actually here, things are a bit more pessimistic. It's very, very modest, but I get 3 to 2 odds that intelligent life is a rarity. So it slightly favors intelligent life being a rarity. And really the reason to understand that is because, look, it took 4 billion years. If it was a simple, quick process, then it's kind of odd that it took 4 billion years. It should have happened much faster. It kind of ate up the entire timescale. A related idea to this, I'm happy to talk more about it, is Brandon Carter's written about this in the past as well, and how the evolutionary timescale of the sun, 5 billion years, is curiously coincidental with the evolutionary timescale of ourselves. And there's no reason why those two numbers should be the same. There's no reason why the sun's rate of evolution has anything to do with the evolution of life on the Earth. And yet those two numbers are suspiciously close to each other. So Brandon Carter similarly uses this as an argument for pessimism. So this is why we don't learn much about this from one data point, but it just pushes the needle very slightly towards pessimism. Okay, so that's all I want to say about FI and FL, although I'm happy to ask questions more about it. And I want to sort of use this one data point in a different way now and talk about another term, the Drake equation. And this was another paper which I wrote quite recently with Adam Frank here and Caleb Scharf. And we were interested in the longevity of civilizations. And again, we do have a data point, how long it happened on the Earth. And our existence is not predicated on it being a specific number. You know, there is obviously a very weak data point here, but unlike abiogenesis, it doesn't have to be a certain value or outcome for us to exist, or at least there's not a strong argument as to why, as there is with the abiogenesis case. So for the case of FL, what we were able to do is use this Poisson process as an argument, but that's not going to work here. It doesn't make any sense to assume that L is a Poisson distribution. For one thing, it's a continuous variable. It's not an integer. So you wouldn't use an integer distribution for this. So we don't know what this distribution is, and we have to assume something for it to make progress. And yeah, I was talking to Barry about exactly the same thing earlier on with his work as well. So what we assumed in our paper was we looked at the geological record again for guidance, and we noted that the species lifetime on Earth is an exponential. So if you look at the fossil evidence for how long different species survive through the eons, you find that there are very few species which last hundreds of millions of years, very few. But there are lots and lots of species which last for just a few million years. And then they disappear from the geological record. And that makes perfect sense because they're failed evolutionary experiments. They're realizations, configurations of life that just wasn't particularly adaptable and just wasn't particularly successful. And it makes perfect sense in a Darwinian process that you would end up with way more failed cases than highly successful cases, because you know it's an iterative process of converging towards those successful instances. So you see this empirically. I mean, this isn't a simulation. This is empirical data from fossils that there's this exponential-like distribution. Weirdly, you kind of see, I think you can kind of make the same argument for human civilizations. I'm not an archaeologist by any means, but it is interesting to grab this data and have a look at it. It doesn't look, when you plot it like this, actually, it's a nice graphic, but it doesn't show the exponential nature. But you can see that there are a few long-lived civilizations lasting hundreds, even 1,000 years. And then there are, you know, some far more of the short-lived civilizations, at least in the human record that we know about. And this also is quasi-exponential. It's a highly incomplete data set, and we didn't attempt to regress to this data. We didn't attempt to do any statistical inference on it, but I think we have two lines of argument as to why an exponential is reasonable. It's also very compact. It's a single parameter distribution, and so by Occam's razor, you'd always try to use the simplest thing you can get away with. And the nice property about it is that it has this constant hazard rate. So you're basically saying, like the Poisson distribution has this uniform rate process, an exponential distribution has a uniform hazard rate. In other words, in each time interval, the probability of extinguishing yourself is the same. So you're just as likely to go extinct from time equals 1,000 years to 1,100 as 1,100 to 1,200. This is a uniform rate. So that could be like an asteroid impact, GRB, supernova, whatever, when we're thinking about technological civilizations. So we can pretty much play the same trick as I showed you before. I'll go a little bit quicker through it, but we can write down a reference prior using the Jeffreys technique for this distribution. We can apply it, we can get our posteriors. And the one thing we don't know, whenever you have an exponential, it's characterized by a mean rate. So for instance, if you look at uranium, it has a mean rate of about 4 billion years, I think, for the decay rate of a uranium atom. So it has that tau, that's its tau parameter, the mean time scale. Here we don't know the mean time scale of this process, but we're trying to infer it. And when we try to infer it, we get the posterior that you can see in solid, just from our one data point. I'm being very ambiguous with our age. We just call our age A Earth, because how do you even define that? Is that when we started radio? Is that when we started farming? I don't know. So we just called it a symbol, and then everything's relative to our own age in what follows. Now, the key, we've talked about selection bias before, and there's a really important selection bias here that we call temporal bias that really plays a big role in thinking about our place in the universe and our place in the galaxy, I think, when we talk about life. And it's what we call temporal bias. So I'm sorry if we should have thought more about the color scheme here. We've got red and green. I apologize for those who can't distinguish these very easily, but each green dot here corresponds to a young-lived civilization that is being born in the galaxy. And each red dot is a long-lived civilization that is being born. And in this simulation, I'm spawning an equal number of short-lived civilizations as long-lived ones. There's a 50-50 more or less balance between the two. So this seems to be working, but if you look closely, you might notice that there seem to be more red dots on the screen than green dots. You might be able to notice that. And in fact, if we make a histogram of it, you can see it. There are way, way more, at any one instance of time, there are way more red dots than green dots. And the answer is kind of obvious. The red dots live longer. So even though I'm spawning just as many of the two, the fact they hang around so long means in any one snapshot in time, I have an overabundance of these things. And so this is going to actually play a really important role when we think about longevities of civilizations and who might be out there in the galaxy right now. So we did this in this paper, and we sort of argued that, I mean, the titles may be a bit over sensationalized, I think, in hindsight. I kind of regret it, but we called it contact inequality. And the idea was that there's probably more, even if you have an intrinsic population, like shown on the left here, where half of the civilizations live for just as long as we did or less, and then there's a tail of very long-lived civilizations. Because of that temporal bias, you greatly squeeze down this distribution, and you end up with quite a lot of the long-lived civilizations left. In fact, the ratio boosting factor is like 3.5 in this example. The conclusion of this was that when we think about SETI, we should be a bit skeptical of the idea of using radio and using the technology that we depend on, and that civilizations out there could be far, far older than us, which really begs the question whether they would even be interested in us whatsoever. You know, like, how long do you spend trying to talk to ants in the street? So people have made this argument many times before. We sort of rigorously showed it, I think, in the statistical framework. There's a good reason, no matter what you assume about this distribution, this temporal bias effect pushes it in this way. The other thing I want to highlight about this temporal bias, it creeps into the n term in the Drake equation as well. So n is the mean number of civilizations in the galaxy right now that are communicative in Drake's version. But people often don't say mean, they just say it's the number. It's actually very hard to find any references that call it the mean number. It's almost always called the number, but that doesn't make any sense, right? If these numbers, the average rate of star formation, the average fraction of planets, that would imply these are all just scalars. You put them in and you always have the exact same number of civilizations in the galaxy at any one moment in time. This is a mean. This isn't a particular realization. And so if we're being honest, we would expect it to be some stochastic process again, where at any one snapshot in time, the number of civilizations in the galaxy is bouncing back and forth around some average, which is n in Drake's equation. And so just by counting statistics, you can trivially show that it must be a Poisson distribution. The n in Drake's equation is a Poisson. Again, we keep hearing about this Poisson coming up and up. It's all over the place in nature, the Poisson. So we have this reason such as a Poisson, and that has an interesting implication, because let's suppose the mean rate was 3. So there's on average 3 civilizations in the galaxy at any one moment in time, just for fun. Now, what that would mean is there's a pretty good possibility of getting 4, right? 4 is a pretty high, it's not quite the peak, but it's pretty close to the peak. And so we'd have a galaxy with 4 civilizations, and that is just as likely as a galaxy with 2 realizations. If we chose random snapshots in time, as long as this rate itself isn't evolving in time, which is an intrinsic assumption here. So I'm really thinking about times less than, maybe 1 billion years, where the galaxy barely changes. So we look at sort of modest or intermediate timescales. We'd expect these 2 realizations to be equally likely, but of course, you are twice as likely to be born in this galaxy than you are in the former, all things being equal. So this sort of also scoops the Drake equation a bit, and it means that you are most likely to live in a crowded era than a sparse era. Is another way of thinking about it. So this is a very, very new thought. I haven't written this up anywhere. It's just sort of a thought that came together when I was putting together these slides that I thought was fun to share with you with this in mind. And the other thing I want to highlight is that there's clearly way more extinct civilizations than extant civilizations. Just whatever numbers you put into the Drake equation, you're always going to end up with way more in the past than present. And so many of us and my colleagues interested in SETI have been thinking a lot about what do very long-lived civilizations look like, and what do their relics look like? They might be long gone, but how do you leave a time capsule or some message or some record of your existence that can survive not just millions of years, but billions of years? How do you construct something like that? And should that be informing the way we conduct our own searches? Maybe I kind of feel like it's over-optimistic to think that we're ever going to have contemporaneous contact, but a relic relaxes things a lot more in terms of the contrivance of having all these civilizations packed together. The final thing I promised you was, for the last 5 minutes, is just to talk about applying these ideas more generally. So I've talked a lot about astrobiology because frankly, I love it. I think it's a really fun topic, it's a very engaging topic, but everything I've talked about is a one-off: life, intelligence, at lifetime of our civilization. And these ideas can be applied, of course, to any one-off, such as Oumuamua, or the first pulsar detection, or the first FRB detection, things like this. And so you might call these black swans. There's actually interesting literature about black swan theory from the statistical side. So I wanted to just sort of apply these ideas to these more general cases. And I have to say, it's way easier because there's no selection bias. Our existence does not depend on Oumuamua being detected or not, right? Which was not true when we were talking about these astrobiology questions, where clearly our existence was predicated upon a success. Now there's selection, but if you want to infer, say, the true rate of Oumuamuas in the galaxy, that is absolutely in effect scooped by selection effects. Definitely care about selection effect there, the telescope selection effect. But if you're just asking the direct question, I've been staring at the sky with this telescope for 10 days and I detected this thing. If I don't change anything else, I just use this same telescope, same survey mode for another 100 days, how many more of these things do I expect to detect? There's no selection effect issue there because nothing's changing. So even if there is a biases, you're not seeing all of the Oumuamuas in the universe, you can still reasonably calculate the rate at which you will detect them because those biases haven't changed. Now, the reason why I think this is important is because we're moving into an era where this is going to become more of a thing, I think, because look at TESS, look at Gaia, look at, we have W first, LSST on the way. And we're moving into this era where the survey modes are basically predestined. They're pre-chosen before the mission flies. We're going to do this strategy. We're going to tile the sky. We're going to collect this data. And the sensitivity doesn't, no one goes to the telescopes and significantly upgrades it. They tend to run this mode for many years at a time. And so if you detect something interesting in the first 6 months or the first 1,000 stars or whatever it is, how can you use that one detection to say about future possibilities? The Boyajian star is kind of a fun example of this as well, which I highlight here, which is found through Kepler. I'm going to frame this in terms of time. T1 is going to be the time at which I detect my first black swan. But very generally, this could be anything. This could be the number of targets you've looked at, the CPU load you've spent on it, the effort load, like the number of undergrads you used to scout through data, whatever it is you're using. You can replace T1 with just effort. So, but I am going to frame it in terms of time and what follows. So again, it's just going to be, we can use Poisson statistics to make progress here. You might be skeptical about the Poisson case. In some cases, it's actually valid to be skeptical about it. But if we think of the entire sky, the entire celestial sphere around us, yes, an individual source of, say, FRBs is non-Poissonian, but the entire illumination of FRBs onto the Earth, this FRB doesn't know anything about this FRB over here. So in that case, these are independent stochastic events, and so they have to follow a Poisson distribution as long as they're not talking to each other, they're not influencing each other. So in that case, you can make progress and you can use this Poisson distribution. We're going to basically very quickly follow what we did before. I'll come to the question right at the end because I'm almost finished. I'm just going to ask 2 questions here. 1, can I infer the posterior distribution of lambda? So lambda here is the rate of whatever event it is, the rate of Oumuamuas that you detect in your survey, the rate of Boyajian stars that you detect in your survey, whatever it is. And T2 is the time when I get a recurrence. What is the probability distribution of the recurrence time given the first time, T1? So we can actually make mathematical progress on both of these. Here are the results. You get this very long-tailed distribution for the recurrence time. And this is really interesting because it means that you can actually observe a very long time. So for example, you can observe for 9 T1, and you have only a 90% chance of re-observing. There's a 10% chance you won't observe anything again, even after doing an order of magnitude more observing. And a lot of people, I think, you look in the literature, they tend to give up after 2 or 3. After 2 or 3 times, if they don't see it repeat, they tend to think, I'm not going to get a hit. But actually, it's quite likely, well, not likely, but it's not implausible that after an order of magnitude more, you won't see it again. Maybe an example of this, I was just chatting, I just added this slide in last minute. Ting Li and I were chatting and talking about this hypervelocity star detected from 4 days of data. And I think Ting Li told me they had 50 days of data now and still don't see it. But I calculated that that's a 7.4% probability. So it's not that, it's not that unusual. And I think it would still be worth continuing to observe with those kind of odds. It's not that strange that you haven't re-observed another example at that point. The other thing we can do is talk about a benefit to cost ratio. This is like an economical analysis. If my telescope time has some cost associated with it, continuing the survey has some cost, or continuing my CPU loads has some cost, presumably it's proportional to the effort load itself, T1. And so you can optimize, or not really optimize, but characterize how the benefit to cost ratio drops off. This is somewhat sensitive to how you define the value of a detection. So if the first detection was Nobel Prize worthy, what is the value of the second one? Is it half as much? Is it a third as much? How do you define that? There's a few different models I tried here, some of them very pessimistic, some optimistic. The takeaway is that pretty much whatever you assume, it's usually profitable to continue for up to an order of magnitude longer than the original survey. You're still likely to end up scientifically profitable in this economical analysis. So I'm going to finish there because I'm at 2:55. And what I want to say, some takeaways, is that be open to the possibility of loneliness. It's not a popular view, but I think it's one we should be open to. The data is absolutely not compelling either way at this point, although there is, I have to say, some weak evidence that there's cause for optimism for life re-emerging. For intelligence, we have no idea. However, if there are civilizations out there, there are some interesting games you can play with a longevity factor, such as the fact we're probably one of the younger civilizations in the galaxy due to this temporal bias effect. We should think about that when we do SETI surveys. And yet more, we're probably outnumbered by extinct civilizations. There's probably a lot more dead civilizations than living civilizations. And finally, when it comes to black swans more generally, my takeaway is be patient. Order of magnitude rule. If you observe for 10 times longer than your initial survey, you still have a 10% chance of not seeing it. If you observe for 2 orders of magnitude longer than your original survey, there's still a 1% chance you won't observe it. So you need a lot of patience going after these black swans, but it's often worth it. Thank you.
Okay, well, thank you, David. There's a lot to think about there. I don't know really where to start. So maybe if we have time for a couple questions, though. Who do I have at the top? Let's Alex, maybe ask the first question.
Hi, David. I have a question about the sort of the statement that of objectiveness and the priors canceling out in the analysis that you did for that first section. Isn't that really just saying that, I mean, like, you know, you end up with a likelihood ratio, which because your priors canceled out, but isn't that really just saying that the 2 models that you're comparing had the same prior, like you treated them equally? I guess I don't understand the distinction between that.
Yeah, so there's 2 different types of priors. There's the prior on the models you're comparing, which is what you're describing there. So you're saying, what is the prior probability between the 2 models?
Yeah.
And so if I wanted to calculate an odds ratio, it would be the Bayes factor multiplied by the prior probability ratio.
Yeah.
Right. But I actually didn't calculate the odds ratio. I only calculated the Bayes factor. And the Bayes factor is specifically designed in a way to basically avoid the discussion of what the prior ratio is between those 2 models. Although coincidentally, it is true that with the Haldane perspective, those do have exactly equal weights. But that's not built into the statement that the Bayes of what the Bayes factor is.
Okay, I see. Okay, so it's about the base. It's about the Bayes factor, not about the conclusion that you draw from.
Yeah.
Okay.
But yeah, personally, maybe I was being a bit implicit there and lazy, but I certainly do feel comfortable with applying a priori even odds to these 4 corners. And maybe I was implicit about that and should have been clearer.
Okay, thanks.
But rigorously, I only defined the Bayes factor.
Other questions? I mean, about one question I had, but maybe I was just getting confused, was there a logical disconnect between sort of the first part of your talk and the conclusions in the second part, in the sense that this conclusion that there's going to be a lot of extinct civilizations, is that consistent with your priors that you were using, you know, these 4 corners? Or is that picking out some of those corners to assume that, you know, you're in that situation?
I mean, I would only say with that, maybe I should be clearer again there, that I may mean the ratio. So I can only say the ratio of extinct to extant civilizations has to be, I mean, you can basically make it 1. You could make it 1, or you can make it a number much larger than 1, but you can't make it a number less than 1. You can't make it so that there are more, because I guess in extinct, we're kind of including the living as well to a certain degree. It's like a cumulative, right? It's all from time equals 0 up to time equals now, to be a bit clearer about that definition as well. So there's no way, you know, let's say with the only instance of success, then there's 1, and there was ever 1. So the ratio is 1 in that case. But whatever you do with the Drake equation, you can only make that ratio larger than 1. You can't ever make it smaller than 1, which obviously makes perfect sense intuitionally. So I don't know that, I mean, it's quite possible that indeed there was no other successes ever in the galaxy's history. All I'm saying is that in terms of like stacking the deck, if you're trying to optimize a strategy for how to get success, I think you're going to be more, I would be more optimistic about finding evidence for a past civilization than one that just happens to be contemporaneous, happens to be using the same radio technology we're using, you're asking for a lot of alignments in a temporal sense, not just even a spatial sense, but a temporal sense. Whereas you kind of marginalize over that parameter, essentially, if you consider everything in the past as well.
But just to follow up, if you're looking instead for past civilizations, would looking for evidence of lower, less advanced technology make more sense, because all of these civilizations would have at least passed through that, even though many of them maybe did not reach the more advanced stages?
Yeah, certainly. I mean, depends on how prominent their signatures would be as a function of time, of course, which is not well defined or mapped out. Maybe short-lived civilizations don't leave much of an imprint. But on the other hand, a short-lived civilization probably is not sustainable. Like, we're probably not very sustainable right now. And so you're probably going to have the biggest effect on the climate of your planet, and the balance with the natural processes that the planet should have, by being this James Dean of a civilization that just burns through everything pretty quick. So it might be that yeah. So I hadn't talked about that, but those are interesting thoughts. I'd love to think more about that. And I think the question of longevity is really important when we talk about strategies for searching.
Does anybody have a final question?
May I ask one?
Yeah, go ahead, Barry.
Well, when you were discussing the longevity of civilizations historically on the Earth, those are sub-civilizations. They were not civilization. Yeah. And you mentioned that they destroyed themselves. Some of them did, but some of them were destroyed by other civilizations impacting on them. Mm-hmm. Okay, so that's just one aspect of it. But it's possible to have a civilization on another planet disappear, but it could regenerate. So you could have a planet which is long-lived, producing many civilizations, or several at least, making the planet a long-lived civilization holder with still having them die off.
Yeah, I totally agree. It's a really interesting extra layer of complexity to add into this that is not accounted for in what I've said.
Yeah.
And I don't really have a good way of, but I have to think about it more. I don't really have a good way of building that into what we've done so far. But I think it's a completely valid and reasonable point that you would expect some fraction of these to reemerge, depending on the level of cataclysm, but you'd expect some fraction.
And then on top of that, there's the proliferation if they disperse.
Right. Yeah, Adam Frank's team at Rochester does a lot of galactic simulations of those kind of scenarios. Mm-hmm. And this is obviously like Hartman's factae, like why
aren't they everywhere?
Yeah, why aren't they everywhere? Yeah.
So I think that's a good place to stop. David has some dinosaur playing to get to, I guess. So we, since the talk slots filled up so quickly today, we did schedule a few more tomorrow. And if you want to follow up with David on any of these topics, please schedule yourself. But otherwise, thank you, David, for a really interesting talk.
Thank you for listening, everyone. We appreciate it.
Thank you very much.
Thank you. That's great.